Now here we look at the case where x of t is equal to minus e to the minus at times u of minus t, okay? So this is a left-sided signal, right? This is non-zero only to the left side of the origin. And it may also, right, if you neglect the negative sign here, right, it can also either grow unbounded or it may also decrease depending on whether a is greater or less than 0. Okay. Now, let's look at the Laplace transform of this. So this is minus the integral of e to the minus at u minus t e to the minus st dt. Okay? So the unit step function limits the integral from minus infinity to 0 of e to the minus s plus a t dt. All right? And this is 1 over s plus a e to the minus s plus a t evaluated at 0 and minus infinity. Okay? So when you substitute e t equal to 0 inside, you get 1 over s plus a. When you substitute minus infinity inside, all right, if you substitute minus infinity inside, then this exponential will either go to infinity or go to 0, right? But for it to exist, it must go to 0, and in that case, s plus a must be negative, okay? So this integral converges to 1 over s plus a when the real part of s plus a is less than 0, or in other words, the real part of s is less than minus a. Okay? And this is the region of convergence. All right. So here we can see that the Laplace transform for this left-sided exponential, right, is equal to 1 over s plus a with the region of convergence including all s whose real part is less than minus a. Okay. So this example further emphasizes the fact that, you must specify the region of convergence in order to have a complete characterization of the Laplace transform. Because if you compare this case with this case, you can see that they both have the same algebraic expression, right? 1 over s plus a. But they actually correspond to completely different signals, okay? And this difference is caused by this region of convergence, specified by the region of convergence, okay? So if you don't specify this, then you don't really know if this is either a left-sided exponential or a right-sided exponential, okay? So to specify the Laplace transform of a signal, both the algebraic expression and the region of convergence must be specified. Okay? And you can see that the algebraic expression is in fact same for examples 9.1 and 9.2, but with different ROC. Okay. Now, the region of convergence, okay, the region of convergence specifies the value of S for which the Laplace transform exists. Okay, so S could be, any number on the complex plane, right? S is in general any complex number. So you're trying to specify what values, what complex numbers could yield a converging Laplace transform. Okay, so this is often best, visualized by plotting this out on the complex plane. Okay, so for this, you're looking at all values of S for which the real part is greater than minus A. So if you look at the complex plane, right, this is the real part, this is the imaginary part. Right, suppose that minus A is this point here, right? So all values of S who has a real part greater than minus A belongs to the region of convergence. So the region of convergence, for example, 9.1 is this plane here to the right of minus A. Okay. So in example 9.1, the region of convergence is the real part of S greater than minus A, and it is this part here. Okay? Now, similarly, for example 9.2, where the real part of S is less than minus A, right? The region of convergence includes the real part of S that is less than minus A. Then the region of convergence is this half plane to the left of minus A. Okay? So these are the regions of convergence. Okay. Now let's look at a slightly more complicated example. Okay. So suppose that now you have two decaying exponentials that are both right-handed. Okay, belong to the positive with non-zero values on the positive axis. Okay. So if we take the Laplace transform of this, we get the integral of 3 e to the minus 2t u of t minus 2 e to the minus t u of t times e to the minus st dt. Okay? We can split this into two integrals, right? The first one is 3 times the integral of e to the minus 2t u of t e to the minus st dt minus 2 times integral e to the minus t u of t e to the minus st dt. Okay. So this is the Laplace transform of this, decaying exponential, right-sided decaying exponential, and this is the Laplace transform of the right-sided decaying exponential. Now, both of these Laplace transforms fit with the form in example 9.1. Right? They both fit into this form here. Okay, so we know what is the Laplace transform for each one of these. So this one is 3 times 1 over s plus 2. And this integral exists when the real part of s is greater than minus 2. Okay? And for the second term, it's 2 times 1 over s plus 1, where this transform exists when the real part of s is greater than minus 1. Okay? So from example 9.1, we know that this integral will be equal to this if the real part of s is greater than minus 2. And this integral will be equal to this if the real part of s is greater than minus 1. But if you want both of them to hold, then you need to take the intersection of these two cases, which is actually this right condition here. Right? The real part of s must be greater than minus 1. Okay? So your region of convergence should be the intersection of the two, which requires the real part of s to be greater than minus 1. Okay? And this is for both terms to hold. Okay? So hence, we get the Fourier transform pair where 3 times e to the minus 2t u of t minus 2 e to the minus t u of t forms a Laplace transform pair with the combination of these two terms, which you can combine together to get s minus 1 over s squared plus 3s plus 2. Okay? And this holds with region of convergence of real part of s greater than minus 1. Okay? So this is obtained by just combining these two terms. All right? Okay. All right, so one more example. So this example is also very similar. Right here we have x of t equal to e to the minus 2t u of t plus e to the minus t cosine 3t u of t. Okay? So the key here is to first use Euler's relation to expand this cosine 3t into two complex exponentials. Right. So the key here is to expand this into e to the minus 2t. Right. So this is 1/2 e to the j 3t plus e to the minus j 3t. Okay? So if you multiply this inside, you get 1/2 e to the minus 1 minus 3j t plus 1/2 e to the minus 1 plus 3j t ut. Okay? Right. So, by Euler's relation, cosine 3t is just 1/2 e to the j 3t plus e to the minus j 3t. So I multiply e to the j 3t with this e to the minus t to get this, right? And e to the minus j 3t times e to the minus t to get this. Okay. All right, so now we have three exponentials right-sided because they're multiplied by u of t. So all three of these fit with the form in example 9.1. So again, we can directly obtain the Laplace transform which is 1 over s plus 2 plus 1/2, 1 over s plus 1 minus 3j plus 1/2, 1 over s plus 1 plus 3j. Okay? Now, each term has its different region of convergence. Right? So for this one, the real part of s must be greater than minus 2. For this, the real part of s must be greater than the real part of a, which is minus 1. And for this, real part of s must be greater than the real part of a, which is, again, minus the real part of a, which is minus 1. Okay. Now, for all these three terms to hold, you need to take the intersection of them, which gives you a region of convergence that is equal to the real part of s greater than minus 1. Okay? So for all three terms to hold. Okay. So in conclusion, we get a Laplace transform pair where e to the minus 2t u of t plus e to the minus t cosine 3t u of t forms a Laplace transform pair with the combination of these three. Okay, so let me write this out directly. So this will give us 2s squared plus 5s plus 12 over s squared plus 2s plus 10 times s plus 2. Okay? And the region of convergence is the real part of s greater than minus 1. Okay. All right, so from these few examples here, you can see that, in these few examples, the Laplace transform just so happens to take on the form of a, rational, just so happens to take on this rational form, okay? And in fact, whenever you have signals x of t that are linear combinations of these either real or complex exponentials, right, you will generally have Laplace transforms that take on such a rational form. Okay, so rational forms will arise in many cases. Okay. Now, if we focus particularly on these Laplace transforms with rational form, okay, then this Laplace transform x of s in general you can view as some polynomial of s, right, in the numerator divided by some polynomial of s in the denominator. Okay, so for this polynomial in the numerator, the roots we call zeros, right? Because if you substitute the roots of s, the roots of n of s inside x of s would be 0, right? So the roots of n of s are called zeros, and the roots of d of s are called poles, right? Now, if you substitute the roots of d of s inside x of s, then x of s will become infinity, will become unbounded, non-convergent, okay? So basically, this Laplace transform would not exist at the poles or at the roots of the denominator, right? So the roots of the numerator polynomial are called zeros, and the roots of the polynomial in the denominator are called poles, right? So these two values are very important for Laplace transforms that take on this rational form. All right. Now, in fact, right, if you think about it, if the Laplace transform takes on this rational form, then the Laplace transform is specified to within a scale factor, right, with some constant factor, by the poles and zeros, as well as the region of convergence of this transform. Okay, so if you can specify the poles, the zeros, and also the region of convergence, you have basically specified the Laplace transform up to some constant scale. Okay? So, right, to characterize